Okay, I think we can start, Bob.
Okay.
Okay, thank you to everybody for attending to this GMI webinar. Today we try to introduce ourselves. With me there is Bob Johnson. Bob Johnson is has an old career in Kraus Heinz, and of course, I worked in different companies as sales management positions, and finally now is based in Houston. He's the owner, president of Source IEX, distributor of GMI, and also, of course, has performed a lot inspection for clients in its works and both for offshore and onshore activities. Has a very long experience, and we try to explain the topic of today, which are the fundamental for EX. Myself is Andras Plor. I'm a global account manager in GMI. I have a 20 experience in middle-sized company for machine and process automation. And now I'm responsible for main accounts at the GMI and also functional safety engineer. Okay, let's go to the next slides. So let us introduce a little bit GMI. What is this company? GMI is a company that design and produce intrinsically safe and SIL certified devices for main automation packages for DCS, ESD, foreign gas. We are in the market, critical market, I mean critical for application like oil and gas, petrochemical, pharmaceutical, fertilizer, mining, food. GMI started in 1993, but our former company was Econ Instruments, so we have more than 40 experience. We produce complete in our facility in Europe, specifically in Italy, Milan. But we do have also global presence all over the world through our offices in all continents. Okay, next slide. And as we say, just about our production, we have complete traceability for incoming and outgoing products, full testing. So every single unit you can use and from GMI are tested. So there is a test report. So we have also highly automated manufacturing process with SM&D machines. We are also, of course, ROS and REACH compliant, and also SC3 certification is available also for the design. And it is mandatory with the new edition of IS 661 Okay, next slide. And this is a product we do. We produce mainly intrinsically safe isolators or barriers. Let's call it barriers, but isolators. SIL safety release, SIL isolator for non-hazardous application. SIL rated power supply, this is also our specialty. And the multiplexer for zone 1 application. Termination board for application with the DCS, mostly wide DCS and the PLC in the market, hard multiplexer, surge protection, indicators, and also we provide functional safety engineer and EX trainings and services. Next slide. So that is about our organization. We have 10 offices all over the world. There are a lot of authorized distributors in the country where we don't have our subsidiary. More or less 200 people, total staff, 18 functional safety courses per year, and more than 1,000 installations in all continents. Some of our customers divided by system vendors, EPC, OEM, and end users. You may find, of course, a company where you are working also. And of course, we are also very well specified through different end users. Thank you. That's for now. And I'll leave Bob the topic of today. If you have any questions, just as Bob said, you can write on Q&A button. We try to stop time by time Bob during his presentation. Thank you, Bob.
Thank you, Andrea. Well, good morning, good afternoon, good evening, wherever you guys are located. So if you've been to some of our webinars in the past, some of this is going to be a little bit redundant because we've talked about how to understand an EX wall chart. We've talked about things like competency requirements. We've talked about updates to standards. So now we're getting down to kind of the nitty gritty. Just what are the fundamentals of EX? So again, some of this may be a little bit redundant, and some of you folks may have, this may be something that you really have not really had exposure to. So I understand that hopefully this will be beneficial for all of you, and we want to try to answer your questions as we go along. So the first thing we need to understand when we're talking about fundamentals of EX, what are the hazards? And basically in the world, and this isn't just to international standards, either IEC standards or EN standards, we want to classify the explosive atmospheres based upon the type of material that potentially is explosive. And so generally speaking, we divide them into three different groups or categories, or however you want to put it, three different explosive atmospheres. The first one is our gases and vapors and mists that we typically would find in a lot of petrochemical facilities, offshore oil platforms, paint spray booth type applications. We could find those in pharmaceutical plants. The second one that a lot of people sometimes forget but can be extremely dangerous is combustible dust. We will typically find these types of environments maybe in grain elevators. We'll find these in a lot of process facilities. Sometimes we can find these in refineries as well with coke dust. Certainly mining applications, we find combustible dust. And then finally, ignitable solid particles. And what differentiates ignitable solid particles from dust is, generally speaking, these are more like maybe wood shavings or something like that, where we don't necessarily have an explosion per se, but we have a flash fire type situation. So we want to divide, in effect, and understand better the explosive atmosphere in which we're dealing with. So flammable and combustible liquids, and we're going to spend most of our time really talking about gases and vapors because we can go down and talk a lot about dust and everything else, but I assume most people here are probably in the petrochemical industry. So this is going to be the most common type of explosive atmosphere that you're going to run into. So flammable and combustible liquids can produce gases or vapors which are also combustible. They can be easily ignitable and very dangerous. They spread quickly and widely. All flammable liquids which are at or above their flash point will give off combustible vapors. So this is an important term to understand. Flash point. What is flash point? It is that temperature in which an ignitable amount of gas is emitted from a liquid. Some people misinterpret the term flash point as that they think that that's actually the ignition temperature of the gas. It is a separate temperature. The flash point is always higher, or excuse me, it's always lower than the ignition temperature of the gas. The ignition temperature, however, and sometimes we'll call this the auto ignition temperature, that's the temperature in which a gas will spontaneously ignite. So there are two different terms that we want to try to keep in the back of our mind. Understand again, flash point is when a liquid starts to become a vapor that emits enough in which we can ignite. Ignition temperature is that temperature in which we will ignite it. So think of it this way: if we're storing a flammable liquid inside of, say, a tank farm or something like that, the flash point is that area that's generally going to be at the top of the tank when the tank isn't full. That's going to be that area in which that liquid starts to become a gas or vapor, and that temperature is the actual point in which it does. So combustible dust, even though I said I wasn't going to talk too much about it, but there are different types of combustible dust. There are metal dust, aluminum, magnesium. I was talking with a client yesterday. They've got an application where they have to deal with titanium. And titanium and metal dusts are very difficult to deal with because they are conductive. So when they land on electrical surfaces or potential conductive surfaces where they're current, they obviously can create a path and very easily ignite. So metal dust we typically deal with somewhat differently. We consider those the most onerous type of dust. But other types of dust, we have carbonation dust, which are things like coal, carbon black. And then the most common are the flour, the grain, some of the plastics and chemicals. And then only dust with stable oxides will not be combustible. So getting back to the basics and the fundamentals is the explosion triangle. And you've probably all seen this in some way, shape, or form. So in order to have an explosion, we have to have three legs of this triangle. And it's important to remember because when we start talking about the various protection concepts, we have to address one or more of these legs in some way, shape, or form. So if we always keep in mind this explosion triangle, then we start looking at the protection concepts, which we'll talk about here in a little bit. We're dealing with this triangle in one way, shape, or form. So the explosive material could be the gas, vapors, mist, fibers, dust, whatever it is. The source of ignition, that could be all different kinds of things, which we're going to talk about here in just a second. All different kinds of energy sources can be a potential source of ignition. We typically think of electrical equipment as generally it's the arcing and sparking of those electrical equipment pieces making or breaking contacts. But as we'll show you, there's a lot of different potential sources of ignition that we have to take into account. And finally, we need to have some sort of air or oxygen or some particular oxidizer in conjunction with the explosive materials. If we think about gas explosions, pure gas generally will not ignite if it's above what is called the upper flammable limit. But when we introduce oxygen or air into that environment, when we start getting a ratio between the flammable gas air mixture and air, that's when we start running into issues. So pure explosive material in and of itself, generally, unless we introduce oxygen or air, will not ignite, generally speaking. But we take that into account as well. So what are the ignition sources? What are the ones that we commonly see in industry? And these are all referenced in the relevant international standards. And these all have to be addressed in some way, shape, or form. So one of the most common ones are the hot surfaces, things like transformers or light fittings or a motor or something like that. Obviously, there's some examples there: bearings, engine exhaust, broken or damaged parts, friction, lightning, right? Those are potential hot surfaces, or those are things that will ignite the flammable gas based upon the heat. Obviously, things like open flames, fires, cutting torches, cigarette lighters, pilot lights. This is why we say, in order to go into a hazardous location and you want to do something using power tools or do any welding or doing any cutting, we have to make sure that we do our gas-free permits. We have to make sure that there's no gas in the environment before we do any work. Some of the other things, however, are things that maybe sometimes don't get thought about, but are certainly important to remember. Things like mechanical sparks, cutting and grinding, even a drop tool. There are certain tools, and I think we have a question, and I have something on this on the slides at the very end, talking about bringing tools into hazardous locations. And even a thermite action, where you have potentially types of materials when they hit each other, you can actually create enough energy to create a spark, which could be a source of ignition. Some of the other things, obviously stray electrical currents under welding or electrical faults, which we would commonly think about with arcing and sparking devices. However, static electricity is certainly a big issue as well. When we have a buildup of potential static on surfaces and then it automatically gets released, then all of a sudden we can have a situation where, again, it can ignite. Things like the movement of materials, say pouring dust or flowing liquids, all of those types of things can create all kinds of issues with static electricity. And static is one of those things where I think a lot of people fail to really truly take into account. And it's an important issue that you don't want to forget about. Radio frequency, those potentially can be potential sources of ignition. So we have to take that into account, not just arcing and sparking, but the RF. Things like batteries, when we take batteries into hazardous locations, we can short these out. And so things like torches and hand lamps, we have to be very careful about those types of products when we bring those into. Even our keys, the starter that we have or remote start for our cars or unlock key fob, we have to be very careful about addressing those in hazardous locations. Things like radiation, ultrasonics, exothermic reactions, those are also issues that we have to take into consideration. We talk about that, the big explosion in Beirut with regards to that leveling of the port area, and that seemed to be potentially could be an exothermic reaction, or it could have been the fireworks that were igniting it. But certainly a degradation of various things, like the fertilizer that you will see stored in various facilities, we can actually have an exothermic reaction that can cause a spontaneous ignition and explosion. So these are all ignition sources that we have to think about with regards to hazardous locations, and we want to make sure that we address them in some way, shape, or form. So when we talk about gases and vapors in particular, there are a slew of different flammable gases and vapors out there. These are just some of the most common ones that we will find. So I've broken them down: hydrogen, methane, propane, ethylene, acetylene, hydrogen sulfide. Right next to them, these are what are called gas groups, based upon how we categorize these gases based upon various characteristics. The ignition temperatures that you see over on the right-hand side, you will notice that a lot of these gases and vapors have extremely high ignition temperatures. So when we think about it, hydrogen, 560 degrees C, that's a very, very high temperature, right? However, as we'll see, it doesn't take an awful lot of energy to ignite hydrogen. So it's a gas that we really definitely have to pay particularly close attention to for a couple different characteristics and a couple different reasons. But every gas out there that you will find will have these characteristics. They'll have ignition temperatures. And when we start talking about temperature codes for selection of electrical equipment, this is an important information that we need to understand. As I mentioned just a moment ago, ignition energy is also a very critical thing. And this is one of the reasons why we subdivide gases and vapors into different gas groups. If you notice hydrogen there, which is considered to be a 2C gas, it only takes about 19 microjoules in order to ignite hydrogen. It doesn't take an awful lot of energy. As a matter of fact, if you actually saw a spark of 19 microjoules, or 20 microjoules or 21 microjoules, you wouldn't actually be able to physically see it. It's that small. It would almost be invisible to the naked eye. So it doesn't take an awful lot of energy to ignite hydrogen. As we see some of the other gases, it takes a little bit more. Propane takes on 260 microjoules. So it's a factor of almost 13 times the amount of energy to ignite propane than it does hydrogen. All of this information is referenced with regards to the ignition energy, the temperature codes. These were all referenced in the IEC 60079-20-1. That's now been replaced by the 80079-20-1. So all gases and vapors that are flammable will show up in that document, and that's where we find this information. Now, this is an interesting slide to take a look at. What we're talking about here, this is actually somewhat of a combination, and I mentioned this briefly about gases and vapors, that they need to have a combination of fuel and air or oxygen in order to potentially ignite. So what you see there, you see two curves. One is hydrogen and one is propane. The hydrogen one, what you see on the left-hand side, basically what we're saying with this is at the far left, when we have a volume of 10% hydrogen, 90% air, that's considered to be the lower flammable limit, meaning that if we have less than 10% hydrogen in the atmosphere and we have an arc or spark, we will not have an explosion. At the high end, we notice it's about 77%, meaning that anywhere, if we have a concentration of somewhere between 10 and 77% hydrogen in the atmosphere, and we have a potential ignition source, we potentially could have an explosion. Now, all gases and vapors also have what is called the minimum energy ignition curve, the MEIC. That's the, or I should say, the most easily ignitable concentration. What that means is that that's the point in which it's the sweet spot, if you will, for all gases and vapors, meaning that that's the point where it takes the least amount of energy to ignite, in this case, hydrogen. So when I mentioned previously on the other slide where it only took about 19 microjoules to ignite hydrogen, we need to have a ratio of about 29% hydrogen and 71% air to have that point, okay? We look at propane over there and we see that propane has a much narrower band, if you will. It doesn't take as much propane to have a source of ignition, but when we have too much propane in the environment, say we have a dramatic release of propane into the atmosphere, if we get above, say, 12 to 14%, somewhere in that range, we have too much propane and we have an arc or spark, we will not have an ignition source, or we will not have an explosion. But it's important to understand these ignition levels, the UEL and the LEL, because all gases and vapors also have characteristics like this. This is another reason why we kind of categorize hydrogen as being one of those gases that is extremely dangerous and very difficult to deal with. So let's see, we have a poll. Oh, wrong poll. Not sure if we have the right poll here. Let's see. Andrea, do you happen to have the right poll?
Let me check.
Well, we may not.
Yeah,
So I tell you what, that's okay.
I can launch.
You can launch it?
Yeah.
Oh, there we go. Okay. So I will give you guys, 30 seconds to answer this question. So I kind of highlighted this a little bit, tried to emphasize what flashpoint is. So you have a choice of four answers. Don't worry, we won't identify you if you get the wrong answer. So that's okay.
Yeah, it's anonymous. Anonymous answer.
So your choices are temperature in which a gas or vapor will spontaneously ignite, temperature in which a flammable liquid will turn into a flammable gas, ignition temperature at which point the gas will explode violently, the point in which a flammable solid would become a liquid. So let's see.
Okay, let's see. I don't see any further answer. We can stop if you like.
Sure, go ahead. Let's share the results.
Okay. Let's share the results.
Yep. So a majority of you guys got the correct answer, which is B. That is that temperature in which a flammable liquid will turn into a flammable gas. A is the ignition temperature. That's, or what we would call the auto ignition temperature. So remember, flashpoint is the point in which a flammable gas will turn into a flammable, a flammable liquid will turn into a flammable gas. Ignition point is that temperature in which it will spontaneously ignite. Okay, so let me close that. We'll continue on. Now, you've probably all seen these T numbers. So when we talk about gases and vapors and we talk about EX equipment, we have to assign temperature codes. So these T codes range anywhere from T6 to T1. So T6 is, from a product standpoint, it is the best from a temperature. From a gas standpoint, it is the most onerous. So let me show you some examples of some of the gases and vapors that we will typically find. So where I mentioned hydrogen, notice that hydrogen in the lower left-hand corner, hydrogen is a 2C gas. It is a T1, it is given a T1 rating. Now what that means, because hydrogen, if you recall, had a very, very high ignition temperature. I think it was 560 degrees C. If we actually go back and look at this slide here, a T1 gas is a gas that has an ignition temperature above 450 degrees C. So if we look at this slide, we see hydrogen is considered to be a T1 gas. Most flammable gases and vapors that you will find in industry will typically be in the T3, T2, or T1 range. However, there are some gases and vapors that are T4, T5, and T6. Again, this is only just a representative sample. You would have different gases and vapors in your facility. So it's important to understand that, but we need to know the T codes when we start applying electrical equipment and mechanical equipment into hazardous locations. So this chart over on the right-hand side, we used this in our little wall chart webinar here a while back, and this is off the GMI wall chart. But trying to explain this in effect, if on the right-hand side you see again some representative gases and vapors, the important point to know, and I'll just try to see if I can highlight this real quick right here. So if a product, if you will, carries a T4 rating, meaning that that product has a relevant surface temperature of 135 degrees, and where I got that information is right off this chart right here. That means that that product will never exceed 135 degrees C under a particular fault condition. Now, what that means is that if we want to place that into an environment, that means that we can use a product that's rated T4 in an environment in which the gases could be T1, T2, T3, or T4. Because if you notice here, ethyl ether 175, that's a T4 gas. However, our product is also rated T4. That means it will not exceed 135 degrees C. Ethyl ether has an ignition temperature or an auto ignition temperature of 175 degrees C. So our electrical equipment, our instrumentation equipment is below the ignition temperature of ethyl ether. Now, as another example, if say, for example, we wanted to take a piece of T4 equipment and put it into an environment that has carbon disulfide. Carbon disulfide is a T6 gas, meaning that it will ignite as soon as the relevant surface achieves 90 degrees C or better. So if we take a product that's rated T4 and we try to put it into a T6 environment, we cannot do that. On the other hand, we can always take a product that's rated T6 and we can put it in any of those environments there. So this is where it gets a little confusing. Sometimes people get it backwards, mixed up, and everything else. But the important thing to remember, if we have a product that's rated T6, we can use it in any environment. If we have a product that's rated T1, we can only use it in a T1 environment. Make sure we remember that. So let me clear those, clear the drawings, and we shall continue on. Another factor that we have to take into account with regards to hazardous locations is the density of the gases and vapors. So all gases and vapors have various densities. Some are lighter than air, some are heavier than air. As we see hydrogen there, hydrogen is much lighter than air. Notice acetylene. Acetylene has the same density as air. One of the reasons why acetylene is very dangerous is that if we have a release of acetylene into the atmosphere, it will basically go anywhere that air goes. So we need to be very, very cognizant of the fact. For example, if we have an enclosed space in which hydrogen potentially could be released, we might categorize the upper area where hydrogen could accumulate as a more onerous area than down near the floor. The opposite would be true with gasoline vapors. So when you go to fill up your car with gasoline or diesel, gasoline vapors are heavier than air, so therefore you're going to find most of the flammable atmosphere is going to be down near your feet. The light fittings and everything right above you could be general purpose lighting because we have plenty of ventilation. So here's just a quick little example. If we had gas detectors based upon the density of the gas, where would we place these gas detectors? And let's see, is this going to work for me? So if we have gases and vapors that are heavier than air, we're obviously going to put our gas detectors in low spots. If we have a release and our gases are lighter than air, say hydrogen, we're going to want to make sure we have our gas detectors located in a location that is going to be able to sense it. And obviously, if we have a vessel that may be containing acetylene that's very similar to the density of air, then we're going to make sure that we put our gas detectors in all locations, quite frankly. So another poll question, getting to our T codes again, see if you guys were paying attention. So what would be the relevant T code for a product that has a maximum relevant surface temperature under a normal or fault condition of 125 degrees C? So you're going to have to kind of remember what those T codes were by memory. So it could either be a T6, T5, T4, T2, T3, T2, or none of the above. And we'll see if you guys really know your T codes. Excellent. You guys are doing good. Fantastic. So I'll give you a hint. The T codes, without giving you the numbers, but the range of numbers is 85, 100, 135, 200, 300, and 450. All right, I think most of you have answered, so let's end the polling and we'll share the results. So we've got a little bit all over the place. We got some T6, T5, T4. So T6 is actually 85 degrees C. T5 is 100 degrees C. T4 is 135 degrees C. Now, the key thing to note in what I was asking here, what is the T code for that product if that temperature will never exceed 125 degrees C? Well, the next highest one from 125 would be 135, which means that the product would actually be marked T4. So a majority of you guys got it correct. T4 would be the appropriate marking for that particular product because that relevant surface temperature will never exceed 135 degrees C. So there you go, 125. Okay, so let's continue on. This is a little bit of a busy slide, and I'm going to skip around through these a little bit, but area classifications, we start classifying them into zones in the international world. So the important thing to remember is that we have basically zone 0 for gases, zone 20 for dust, zone 1, zone 21, zone 2, zone 22. So there's our equipment groups. There's either gas or dust. And then under the IECEX, we also have what are called EPLs. So area classification is done to 60079-10-1 for gases and vapors and 10-2 for dust. And then we continue on here as again, we talk about the surface equipment groups. So we have our groups. And then we have G or D for gases or dust. And then under the IECEX, we have 3 equipment groups, if you will. So the important thing to note is that if we have a particular piece of EX equipment that is rated for zone 0, that means that that product is built with 2 independent means of protection or 2 independent faults. So the products that we can only use in a zone 0, and a zone 0 area is continuously present. So that means there's a flammable gas air mixture or flammable dust mixture in that environment pretty much 100% of the time, that we want to make sure that the equipment that we're putting into that environment can withstand 2 independent faults. So therefore, equipment that is designed for zone 0 is generally speaking going to be more expensive, more robust, if you will, than what you would find for, say, pieces of equipment suitable for zone 1 or zone 2. And again, kind of blasting through these slides here. So one other poll question here. So a definition of zone 1, I kind of skipped through this slide, so you're going to have to somewhat guess. But I did say that a zone 0 is an area in which a flammable gas air mixture is continuous. Okay. So a zone 1 area, what would you guys think? And you guys are guessing well. And I think a majority of you guys are thinking it's either A or B. And I will say, yes, you are correct. It's either going to be A or B. So for those of you who have not answered yet, pick one of those two. The reason it's not D, because that's a dust hazard, that would not be considered to be a zone 1. It could be a zone 21. So that's the reason why D is not the correct answer. So let's go ahead and end the polling and we'll share the results. And the majority of you guys got it correct. It is B. That is a gas vapor hazardous atmosphere present occasionally during normal operation. So A is actually our zone 0 type environment. C would be a definition of a zone 2. It can happen occasionally, but it occurs infrequently. Okay, so we'll continue on here. So getting into the protection concepts, I'm going to skip through this slide because we're going to talk more about these protection concepts in the next slides. So again, go back to what we talked about with regards to our energy or ignition triangle. When we think about our protection concepts, we want to keep that in mind. And so when we talk about some of these protection concepts, what are we doing with one or more legs of that triangle? So obviously GMI, manufacturer of safety relays, intrinsically safe barriers, etc. This is one of the key protection concepts that they use, which is called intrinsic safety, EXI. So this limits the amount of energy to levels below that minimum ignition energy of the particular gas group environment. So if we think back on that one slide where we saw that we didn't take an awful lot of energy to ignite hydrogen, if you guys recall, it was 19 microjoules or microjoules. That means that the circuit, if you will, coming out of an IS barrier that's suitable for 2C environments in which hydrogen could be present, cannot allow more than that minimum ignition energy to ignite hydrogen. So therefore, as you can see, when we saw that other chart where we saw the amount of energy that it would take to ignite propane versus hydrogen, propane took a lot more energy. So therefore, the let-through current on an IS barrier is actually a little bit higher if it's only suitable for propane as opposed to hydrogen. So what we're doing here with the legs of the triangle, we're basically removing that source of ignition, right? There's no arcing or sparking in effect, or it's of such low energy, it will not ignite any gases or vapors. So that's energy limitation, intrinsic safety. Another protection concept that's widely used is increased safety, EXE. So what we're doing here is that we're eliminating the potential for a spark or arc to occur due to the design of the equipment. So we're taking, in effect, any electrical circuits and we're housing them inside some sort of enclosure in which we use special terminal blocks that are designed to minimize the creepage and clearance distances so we don't have shorting in between those terminals or those circuits. So that whole concept, if we can basically eliminate arcing and sparking in a hazardous area, now we don't have to go with flame proof or some other protection concepts. We can actually go what is called increased safety. Non-sparking, which used to be known as EXNA, is now known as EXEC. It's a lesser form of EXE, and EXE will now be known as EXEB. So for those of you from the looking at EX equipment, you might see products that previously were marked EXE. They will now be marked EXEB. So another concept is containing it. So now we're taking that triangle and we're assuming that we're going to have an ignition source. We're going to have gas-air mixture. We're going to have air, and they're all going to be in contact with each other. So we're going to have an explosion. So the way that we do and deal with it is that we contain it. So flame-proof boxes is a prime example of containing an explosion. So a flame-proof box operates on the principle that we assume we're going to have an explosion on the inside of that enclosure, and the hot flaming gases will cool it off to where it will not ignite the gases surrounding the enclosure, and it will not rupture. It will maintain its strength and integrity. However, there are some other concepts that follow the same principle: powder filled, sand or quartz filled. That's actually a containment process, or an enclosed break, EXNC. So switches that might actually have a hermetically sealed or a small little flame-proof chamber. They contain the explosion and do not allow the hot flaming gases to ignite the gas surrounding the enclosure. And then finally, we get into separation. Separation is now we're removing something from the other legs of the triangle. So encapsulation, we can encapsulate electrical devices. We can hermetically seal it. Pressurization, this is where we're basically saying we're not going to allow a flammable gas-air mixture on the inside next to arcing components. Very, very common method. Oil immersion is that we're taking all of the potential arcing components, immersing them in oil, and then finally restricted breathing. So again, we're removing, in this case, the flammable gas atmosphere from the potential ignition sources, if you will. So again, when we start thinking about these protection concepts in detail, these are the concepts that we use that we have to address that triangle in one way, shape, or form. Now, I'm going to skip this slide because I'm going to actually just use probably a little bit better example. Actually, I'll go to this one first. So this is what you would see on your markings of, say, for example, an EX product. And we'll just kind of go through this real briefly. But what you see right here is this is your ATEX certificate number. This is your CE marking. This is the number for the notified body that actually did the testing. This is our EX hexagon that's telling us it's suitable for hazardous locations. This marking is a requirement under ATEX. So it's above ground applications, what we call category 2, gas and dust. Then right here is the actual marking string for the product. So this product, this is telling us it's a flame-proof product. It's good for all 2B gases plus hydrogen. It will never exceed a T5 rating, which if you recall from your T codes means that the relevant surface on that product will never exceed 100 degrees C at a maximum ambient of plus 55 degrees C. And this GB is telling us, again, it's for a gas atmosphere. And the B is actually telling us that that's our IEC EX EPL telling us that's good for a zone 1 area. So that's our ATEX marking string. This is our IEC EX marking string. And notice this information here is identical to what we see over here. Under IEC EX, this information goes away. That's not a requirement under IEC EX. This is the requirement under IEC EX. Okay. So, let's see. I think we had a question. What does DB mean? Yeah, so D is actually the concept term for flame-proof. And then, so historically, what you would have seen is products without this B. It would just, the old historical markings was EXD. And then here recently with the addition of, I think it was 2017 of the IEC 60079-0, that was where the EPLs were introduced and that protection concepts now had to be marked with that second letter. So it doesn't mean that a product that's out there in the marketplace that's marked EXD and EXD only is no good. It just means that now the product should be marked with this nomenclature, EXDB. And you'll see the same thing with EXEB. You've seen this with intrinsic safety where there was IA, IB, and IC. So now we're starting to see a little bit more detailed information that's being put onto these labels. So going back to this slide here, this is the marking what you would find on a barrier. What you're actually seeing here is a couple different marking strings. This marking string right here is actually telling us a couple things. This is actually telling us that it's suitable for installation into a zone 2 area from our NA and GC, but it's an associated apparatus that is providing downstream protection into a hazardous area, a zone 1 area. So this string right here can be a little bit confusing when people see this, because we see brackets now, we see G, we see EX, NA, and we see brackets IA, GA, 2C, so forth and so on. So if you see that type of marking string, there's basically a couple different meanings into it. But just remember this. If it doesn't have a bracket, that means it can be installed in that area. If it has brackets like this, that means it's providing downstream protection from that device. So that means, in effect, that this barrier can be installed in a zone 2 area, but downstream coming off this barrier can actually be, this circuit can be installed into a zone 0 area based upon this markings right here. Okay. Hopefully that makes sense. So here's I think the last poll question, and it's hopefully a good one. So Andrea, do you have that poll question you could throw up at him? So we have Roman numeral 2, parentheses 1, EXDB, brackets IA, 2C, T6, GB, parentheses GA. What does that mean? It's a lot of stuff. So we just mentioned what DB was, right? So we showed a label of a product, and then we talk about associated apparatus. So IA is intrinsic safety, that's downstream. So our choices are A, is it a flame-proof enclosure suitable for 2C gases located in zone 1 area containing associated apparatus? Okay. Is it B, flame-proof enclosure suitable for 2C gases located in a zone 0 area? Is it C, flame-proof enclosure suitable for 2C gases containing increased safety relays suitable for zone 0? Or is it D, pressurized enclosure, so forth and so on? Well, by process of elimination, D is flame-proof. So we know it's not letter D, or I should say the answer D, it's not a pressurized enclosure. So we know it's a flame-proof enclosure. There's a couple things in there that also tells us why C would not be correct. Increased safety is a protection concept called EXE. I don't see any EXE in the string. And those relays would not be suitable because we don't have EXE in effect inside that enclosure. The thing about B, flame-proof enclosure suitable for 2C gases located in a zone 0 area, that would not be correct because a flame-proof box based upon this GB marking right here, that means it's only to be able to install into a zone 1 area. So the correct answer is A. So looking at what you guys answered, a majority of you guys did, you got the correct answer. So fantastic. That's a tough one. So you did a fantastic job. So just a little bit other stuff that we do have. That's basically the main portion of the presentation today. But we're going to throw up some Q&As here in just a second. So besides just having an EX wall chart, GMI also has a functional safety fundamentals wall chart available. Here's the key things to remember when it talks about EX fundamentals. When we're looking at equipment, don't forget mechanical equipment as well. I understand that many of you on here are probably either instrumentation or electrical folks, and that's great, as well as I am. But what we see in industry is a lot of the potential sources of ignition and a lot of the disasters that we're seeing are actually not necessarily caused by electrical equipment, but are actually caused by mechanical equipment. So to find out more about that, the 80079 standards that are published by ISO and the IEC are now adopted, and we cover basically mechanical standards and requirements for mechanical equipment. Again, the other thing is sources of ignition in hazardous areas are based not only on equipment, but also our own personal actions, right? Bringing in a cell phone into a hazardous location, bringing your key fob into a hazardous location, not doing our lockout tagout, not getting our gas-free permits. We have to be aware of that. So it's not just the equipment, it's our actions within a hazardous area that can also cause many problems. Dust hazards are also just as dangerous. And just remember, we're only as strong as the weakest link. So if you are concerned about anything that you see, speak up. It's important to make sure it's better to be safe than sorry, right? So even though we may not have the responsibility for a particular project or this or that or anything else, but if you feel unsafe in any environment or what have you, speak up, because it's we don't want to be that person that didn't say anything and then all of a sudden something happens and a bunch of our colleagues pass away due to some industrial disaster. So please make sure we do that.
We do have a few questions if you want to
Yeah.
answer.
Yeah, I'll be happy to. So one of the questions, can we explain why the 2G labeling is only used for ATEX? Why? I don't know if I can give you a good answer. I just know that it is a requirement under ATEX, and it's not a requirement under the IEC-EX. So the IEC-EX went to what was called EPLs, and ATEX went to a concept called categories, which is what we see here. That's a category 2G for gas applications. Why that was done that way versus the IEC-EX way, I just honestly don't know. There was a second question also, as you first mentioned, the first part of marking is for ATEX and latter for IEC-EX. I am unclear of the difference in the representations. So yeah, going back, let me go back to that slide again, just to see if I can bring that up again. So again, we have, let me see if I can annotate here. So this information is what is required under the ATEX directive, actually, this as well. So the CE marking and the EX hexagon, this information again is the notified body. This is telling us it's above ground applications. This is called what in the ATEX world we call category, and then gases and dust. So this is all mandated by the ATEX directive and what has to be marked on a particular piece of equipment. This information, GB right here, is basically the IEC-EX version of 2G information right there under the ATEX categories. So this 2G is actually means the exact same thing as GB. This is the requirement under the IEC-EX. Now, actually, in the ATEX world, they now are actually saying it's okay to go ahead and have that marking as well on a piece of EX equipment. However, this is not mandated under ATEX. This is mandated. Under IEC-EX, this is what is mandated, period, end of story. So it's a slightly different thought process. The important thing to remember here is that the products themselves are identical, because the standard in which this was built to, this is built to an IEC standard. So this is IEC 600, so forth and so on. This here is telling us that it was built to an EN standard, which is identical to the IEC standard with regards to the actual technical characteristics. However, there's just different marking requirements and all that good stuff. So the product itself, there's no difference in the product because it's built to an IEC standard to meet this requirement. It's built to an EN standard to meet the ATEX requirements. I apologize for my chicken scratch here. Hopefully that makes sense. All right, so let us clear that
Bob,
and
I
continue
think we
on.
can go through the Q&A.
Yeah, let me bring that up.
Yeah, we do have another presentation dedicated to the Q&A that are, let's say, questions that you made during your registration. So we try to summarize here. Share
Yep.
it, Bob.
Yep, let me bring it up real quick and see if I can bring up my Q&A here.
It's okay. So I think you can see. And
oh, let's see. Is this? Or have
can
you
you
got
see
it?
it?
Oh
Yeah, I
yeah,
got it.
you
Okay,
got it.
yeah. So the first question was, can we open a junction box housing barriers in a running plant if a junction box is in zone 1 or zone 2? Do we use normal tools or some special tools we don't produce parts in oil and gas hazardous zone 1 or zone 2? Oh, good question.
Yeah, it is a good question. So the important thing to note, if the enclosure contains just IS circuits in a hazardous location, the standard does allow the opening of the equipment in hazardous locations without a gas-free or de-energizing the circuit. Now, realize this, the standard does allow you to do that, and that standard is 60079-14. However, certain clients, certain customers, certain local wiring regulations may not allow you to do that. So be careful when I tell you that you can. Realize that that circuit must not be a combination of IS and non-IS. If it has any non-IS circuits in it, then no, we could not open it up. So the other thing to remember is the tools that you bring into that hazardous area, they must be suitable for use in a hazardous area. So if we bring in any electronic meters, it doesn't necessarily mean that the meter itself has to be intrinsically safe, but it needs to be certified to be used on intrinsically safe circuits while energized. So there's a little bit of differentiation there. As far as mechanical tools, there are some specific requirements when we get into zone 0 and zone 1 in particular, zone 0 in particular, that, as I mentioned previously about thermite action or metal hitting some other piece of metal and creating a spark, you will find that there are actually hand tools out there that are actually suitable for use in hazardous locations based upon the material that they use. Typically, it's a beryllium copper of some sort. So you typically have to be careful, even bringing in hand tools into zone 0 type environments. We want to be very careful in those environments about the tools that we bring in.
Okay, fine, Bob. The next question is why EXD are frequently found rather than EX and in marketplace, even though that EXE has many benefits in zone 2 areas, maintenance during process of line, easier to assemble, cheaper, etc.
Yeah. And yeah, that's a great question. And you're finding more and more increased safety out there. I think part of it, the fact is, flameproof has been widely used for many years because a lot of people find it easy to understand, and many different manufacturers offer it. It's a mechanical system, right? You don't have to be an electrical engineer, if you will, to properly select EXD. You know, when you start getting into intrinsic safety, now you have to do some calculations, and that scares people off. So people don't like using IS for various reasons. However, increased safety, what you're finding, because it only allowed non-arcing components in hazardous areas, if you had a contactor or a relay or something like that that was generating electrical sparks, increased safety was just not practical because you just couldn't do it. What you are finding, however, is that there's now component level products such as flame-proof contactors or flame-proof switches or flame-proof relays or encapsulated components that we can now put inside of increased safety enclosures. So we're combining protection techniques into one unit. So you're finding much more sheet metal or plastic type equipment for use in hazardous areas. So I think as time goes on, you'll find more and more of that. But flameproof will still be out there, and a lot of people still use it, even though it's heavy and lots of bolts and all that good stuff.
Good. Next question is EN 50495 standard. How is the relevant safety device required for the safety function of equipment with respect to explosion risk?
Right. So yeah, if you look at this, so this standard is an EN standard. It is safety devices required for safe functioning of equipment with respect to explosion risk. Actually, if you go to the next slide, it's probably a better understanding I put on this one. So a good example might be a motor starter relay. That's a set, if you will, that has adjustable overloads to protect a motor in a hazardous area. So if we look at that little label on that contactor, we notice that it has the EX, the Roman numeral 2, and it has a 2 in brackets and a G. But it doesn't talk about any protection concept. It doesn't say EXD, it doesn't say EXE, it doesn't say EXI. Why is that? Well, that's a safety device that's located in a safe area or could be located inside of a flameproof or pressurized box or whatever, but it is providing protection downstream to coordinate to, say, an EX motor to make sure that it is shut off in the appropriate time. So that's where safety devices come into play. It's basically that standard is saying, look, we need to make sure that if we're using pieces of EX equipment that rely upon some sort of other outside device in order to work safely in a hazardous area, we need to address that. And that's what that standard's all about.
Okay, good. Next question. Several types of EX equipment must be housed in one enclosure for placement in zone 2. What kind of explosion protection of the enclosure should be?
Right. So EXE is considered to be increased safety without any arcing or sparking. EXNA is a lesser version of it. So generally what we would do is that if we had EXE and we want to put various products on the inside of an EXE, all of those products that are inside must be suitable for hazardous locations as well. So unlike on a flameproof box where we can use general purpose electrical equipment, on the inside of EXE enclosures, because the box will not provide any explosion protection other than impact resistance and high IP ratings, the component parts must be EX certified. So I don't know if that answers the question, but I think so, hopefully.
Yeah, sure. Does a humid and corrosive environment affect the EX equipment?
Yes, absolutely. It's important to take into consideration what corrosive or whatever the environment that you're putting EX equipment into. So IP ratings certainly address ingress protection, which we didn't cover here, but that's important to take into account. That's not allowing water or dust to get on the inside of a piece of EX equipment, but also the material selection. So what you see on the right-hand side is actually a picture of a cable gland installed into an aluminum enclosure and that dissimilar metals. So you have to be very concerned about the materials that you're using. You want to take that into account, what seems to work best for one environment. If it's a heavily salt-laden environment or particular corrosive gases and vapors or whatever is in the environment that can eat up electrical equipment, we want to take that into account.
Okay, good, Bob. There is a last question, I think, online. It's
Yeah.
asking again. Can you read it?
Yeah. Yeah, yes, I can see it. The ATEX marking equipment, e.g. Roman numeral 2 will be zone 1. So for ATEX, what is the marking for zone 1 is you would actually find it would be Roman numeral 2. Wait a minute. Yeah, I'm trying to remember here. It would be G for gas applications. Under IECEX, it would be GB. Under the ATEX directive, it would be uh, 2G, if I'm not mistaken. 2G would tell us that it's suitable. That's a category 2, which is the equivalent of a zone 1. So 2G would be the markings that you would find on a piece of equipment that would be suitable under the ATEX directive for zone 1. If it was 3G, that would tell us that it's good for zone 2. If it was 1G, it would be suitable for zone 0.
Good. Thank you, Bob. I think we almost finished, and now is sorry.
Oh,
Okay. So you attended to this webinar. You may find other webinar on our website. We try to promote over LinkedIn new webinar, and also the old ones. So regularly, every say once a week, twice a week, we have different topics to be discussed. You may find also this recording say session. It's in our website. You can look at it again, or maybe you can forward to your people that did not attend. You can find all the other webinars also recorded, so through our YouTube channel. Let us ask about your, let's say, about your opinion about this webinar. So if you can answer, you are anonymous, so you can write whatever you like, but I think Bob will give you a lot of very good information about the PTX and ICX applications. Thank you for your answer.
yeah, it's a lot of information to cover in a very, very short period of time.
Yeah. next time will take 3 hours at least.
Yeah, we do. Just as an FYI, for those of you who are interested, we are working with GMI to set up more formalized training programs under the IECEX Certificate of Personnel Competency Scheme. So we're actually, my company in Houston, we're an IECEX, what is called recognized training provider. And we provide training for those individuals that wish to become competent in EX. And we're rolling this out here with GMI, and we're going to be doing, I think, some of these before with COVID. We're probably going to be doing some of this training online in webinar type formats. So we'll be doing this over hours and days. So if you enjoyed the 1 hour with me like this, you could get me for hours and hours and hours on time. If that's something that you're interested in, we'd be happy to send you some more information on that.
Okay. Thank you very much, Bob. And we end up this webinar. And let me remind you our name, face, emails, whatever you like, if you want to contact us. And thank you very much. Thank you, Bob.
Thank you, Andrea. Have a wonderful afternoon. I think I'll have some more coffee. It's still early.
Yeah, you too, even if it's 12. Right. Okay, thank you, all of you. Bye-bye. Bye.
Bye-bye.